Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today, we're going to talk about the cross product. We need to be a little careful about our notation. There are three products we're going to have now. We have a scalar product where you can multiply a scalar times a vector. We have the Euclidean dot product, and we are about to introduce the cross product. Make sure that you use the correct notation in order to convey which product you're talking about. Juxtaposition is no longer sufficient. If you're talking about vectors, we don't write UV because that leaves it vague as to what exactly you mean. We don't even write U squared. These things are too vague and don't convey any sensible notion. Would U squared be U dot U or U cross U? You see, we can't square vectors. We don't write it in that way, ever. In order to define the cross product, we first need to define what we mean by the determinant of a matrix, a square matrix. What is a matrix to begin with? A matrix is a rectangular array. Notice we have not really assumed that the things that are filling the array are numbers. Suppose the positions for data in the array are like as follows. Arrays don't have to have the same number of elements in each row or in each column. If it is a rectangular array with the same number of elements in each row and each column, then it's a matrix. The order a matrix is an expression of the form m by n, where m is the number of rows and n is the number of columns. You can see that m and n must be natural numbers. A matrix is called square if it has the same number of rows as it has columns. So a square matrix, if it has 3 columns, it must also have 3 rows. For all the purposes for which we will use the concept of a matrix in this class, the entries will be real numbers. Now, in order to define the notion of determinant, I need to start with the determinant of a 2 by 2 square matrix. going to denote the matrix by the capital letter A and its entries by A, B, C, and D. First of all, some notation. When we talk about a determinant, we sometimes write det of A, and even more often, a flat bar on each side of the matrix. Notice that we're using kind of rounded parentheses in describing the matrix. If you replace the parentheses by a flat bar, that implies that you're performing an operation on the matrix called the determinant. It's defined as follows. You multiply down the main diagonal and then subtract the product going the other way. You end up with a real number, a scalar. So when you calculate the determinant of a matrix, you will always end up with a scalar. For example, suppose A is the matrix 2, -1, 3, 5. Then the determinant of A will be 2 times 5 minus 3 times -1. That's 10 plus 3, or 13. To define the notion of determinant for larger matrices requires a few more definitions. A minor of an n by n matrix the determinant of the submatrix obtained by eliminating one row and one column of the original matrix. The minor obtained by eliminating the ith row and jth column is denoted by Mij. For example, suppose the matrix A has entries 2, 1, 3, 5, 2, 1, 4, 7, 8. Then M11 is obtained by crossing out the first column and first row and first column. That is the determinant of the 2 by 2 array 2, 1, 7, 8. Cross out the column and row. That's going to be 16 minus 7, which is 9. M12 is obtained by crossing out the first row and second column. So that leaves 5 and 4, and 1 and 8. Cross out the first row and second column. That's 40 minus 4, which is 36. The ijth cofactor of a matrix is denoted by Cij and defined by Cij is -1 to the power I plus j times the minor Mij. Let me point out that this -1 to the power I plus j in the first entry, first column, first row, in the first row, first column, you get an exponent of 1 plus 1, which is 2, and that gives you a plus. They'll alternate because you get one more factor of -1 each time you bump over a column and bump down a different row. As a consequence, you end up with a checkerboard pattern of pluses and minuses throughout the matrix. These just give you different signs, plus or minus, on these minors. The minors are a determinant, so they yield a scalar. This just associates either a plus or a minus sign according to this checkerboard pattern. So for example, if our matrix A is, say, 2, 1, 3, 4, 7, 5, 6, 8, 9, then C11 will be plus M11, and that is 7, 5, 8, 9 in the determinant. C12 will be minus M12, and so that's minus the determinant that you get by crossing out the first row and second column. First column of what's left is 4 and 6, and then 5 and 9. Well, the first one you get 63 minus 40, which is 23. 36 minus 30 is 6, but we have to affix the minus sign, and so you get minus 6. We're now ready to define what we mean by the determinant of an n by n matrix. Suppose our matrix A has the form A11, A12, over to A1n. Well, the second row will be A21, A22, over to A2n. The last row will be AN1, AN2, terminating in ANN. The determinant of A denoted by flat bars on each side is defined as follows. The determinant of A is, by definition, A11C11 plus A12C12 all the way down to A1nC1n. But it's also, this is called, by the way, cofactor expansion around the first row. These coefficients are all entries in the first row of the matrix A. You don't have to do the cofactor expansion around the first row. In fact, you can do the cofactor expansion around any row or any column, and it is a theorem in linear algebra that you will get the same value whichever row or column you choose. So cofactor expansion around the second row would be A21C21 plus A22C22 plus all the way down to A2nC2n. But you'll get the same thing if you do the cofactor expansion around the first column. That's A11C11 plus A21 C21, all the way down to AN1, CN1, etc. These cofactor expansions are definitely the way that we want to calculate the determinant for the purposes of the cross product that we're getting set to define. There are other ways to calculate the determinant of a matrix if the matrix has specific orders, like a 3 by 3 has a special rule. But in general, you have to resort to the cofactor expansion. I should also mention that this definition is kind of recursive. It defines the determinant of a 3 by 3 matrix in terms of the determinant of 2 by 2 matrices. So a 3 by 3 determinant can be broken down into 3 2 by 2 determinants. Similarly, a 4 by 4 determinant is 4 3 by 3 determinants added up in a cofactor expansion, and those in turn are 3 2 by 2s each. So you can break this down all the way down to 2 by 2 determinants, which we've already defined. So for example, suppose that A is given by the matrix, let's say 3, 4, 1, 2, 0, 2, 4, minus 1, 2. Trying to keep the number small because I don't want to do very much arithmetic. Let's calculate the determinant. It is always to your advantage to expand around any row or column that has as many zeros as possible. That way, you can multiply by a 0. Remember the pattern of pluses and minuses for the cofactors. If we do the cofactor expansion around the second row, because it has a 0, we'll have to affix the pattern minus, plus, and then minus onto the cofactors. So we'll have minus 2 times the determinant of the submatrix that you obtain by crossing out the row and column that contains that 2. So that's going to be 4, 1, negative 1, 2, plus 0 times cofactor here. I'll write it anyway, even though it's irrelevant. Crossing out the second row and second column, you would have 3, 4, 1, 2, like this. Then minus 2, cross out the middle row and last column, that gives you 3, 4, 4, minus 1. So, what do we get? Negative 2 times 8 minus negative 1, that's 9. This is 0. Here we have minus 2 times negative 3 minus 16. What is that, negative 19? The determinant then is going to be negative 18 plus 20 and 18 makes 38, for a grand total of 20. Here we've calculated the determinant by cofactor expansion around the second row. Let's try cofactor expansion around the first row and see if it makes a difference. The determinant of A should also be a positive 3 times its cofactor, 0, 2, negative 1, 2, a minus 4 times its cofactor, first column would be 2, 4, and the second column 2, 2, and then plus 1 times its cofactor, 2, 0, 4, negative 1. You can see that you'll have 3 times 0 minus negative 2. Let me write that out. 0 minus negative 2. Minus 4 times 4 minus 8 plus negative 2 minus 0. So 3 times 2 is 6. I have a running total of 6. 4 minus 8 is negative 4, times 4 is positive 16. So far, that adds up to 22. But then we subtract 2, and that gives us the total of 20. The same as before. It had better turn out that way, or the theorem from linear algebra is wrong. Finally, we're ready to define the cross product. If vector u, which I'm defining to be a, b, c, and vector v, which I'm defining to have entries x, y, and z, are in R3, notice the cross product is only defined for vectors in R3. The cross product of u and v is denoted by u with a conspicuous cross v and defined by u cross v is the determinant of the 3x3 matrix with the first row equal to the vectors I, j, and k. Then A, B, C, X, Y, and Z. So when you're calculating the cross product of vectors u and v, you put the coordinates of the first vector in the product in the second row, and the coordinates of the second vector in the product in the third row. I, j, and k will occupy the first row. Now I am going to teach you efficient means for calculating these cross products. You're going to have to pay close attention to where I put the pointer though at times. I'll give you a kind of hand-waving argument. If you watch closely, this will work and be very, very easy, as you'll see. Let u be the vector 2, 1, 3, and v be the vector 0, 2, 5. I want to find u cross v. We'll do this kind of a slow way the first time around, but then I'll go and show you how to do this very easily. U cross v is I, j, k, 2, 1, 3, 0, 2, 5. That's going to be plus I times the determinant that you get by crossing out the first column and row. That leaves 1, 3, 2, 5. You get a minus on the middle cofactor, plus, minus, plus. Minus j, don't forget the minus, times the determinant of the submatrix 2, 3, 0, 5. Plus k times 2, 1, 0, 2. What do you get? Note that we can switch between the ijk notation and the angle bracket notation. In the first coordinate, I will have 5 minus 6, which is minus 1. On the next entry, you have 10 minus 0, but you have to negate that. So you get minus 10. and then 4 minus 0, and hence you get the vector -1, -10, 4. One thing to point out, when you take the cross product of two vectors in R3, you get, as an output, a vector in R3. You might also be able to see that in R4, you have a problem calculating cross products. If you only have two vectors, you'll only be able to fill 2 rows with the coordinates of those two vectors. But in R4, the 4 by 4 matrix will have 4 rows and 4 columns. So you can only define the cross product between 3 vectors in R4. Also, if you're in R2, you only have x and y coordinates. You may always extend that by including a z coordinate that is equal to 0, and then calculate cross products of vectors in R2. But we're going to allow that. I want to go back and show you how to calculate a cross product without having to write as much as we just did. But you're going to have to pay attention to the hand waving that goes on. So in this case, let's suppose U is 3, 1, 2, and V is 0, 2, 4. Then U cross V will be the determinant of the 3 by 3 matrix IJK 3, 1, 2, 0, 2, 4. What do we get? For the I cofactor, remember you cross out the column containing I and the row containing I and just deal with this lower submatrix in the lower right corner. That's going to be 4 minus 4, which is 0. We get a minus on the middle cofactor. I'll preemptively put a minus here. Cross out the column and row, and you'll get 12 minus 0. And then on the last cofactor, it's plus, and you get 6 minus 0. So the cross product is 0, -12, 6. I hope that's easier. It does require that you followed the waving around of the pen here. Also, now that we've calculated U cross V, let's find V cross U. V cross U, as the first row, of course, IJK. The middle row is now 0, 2, 4, and then 3, 1, 2 for the last row. Let's see what you get. On the I part, you cross out the first column and first row. That's going to be 4 minus 4, which is still 0. In the middle one, don't forget the minus on the cofactor. We'll have 0 minus 12. And then for the last one, you get 0 minus 6. So here we get 0, positive 12, and then negative 6. Do you see the difference? It's very important that you note that U cross V is not the same as V cross U. That means that the cross product is not commutative, and this counterexample proves it. However, it leaves open the question, do you always get the negative when you reverse the order of a cross product? That will be discussed in our theorem on the algebraic properties of the cross product. Remember how we go about this. We'll define the concept, we'll proceduralize it, show you how to implement that concept, then prove a theorem containing algebraic properties, and following that, we'll prove a theorem giving you the geometric properties, which will really tell you why we're doing this. So we need the algebraic properties. course, u cross v will be the negative of v cross u. We will prove this. 2 u cross, we need to explain how the cross product works in relation to the other operations that we have defined, and in particular, with respect to vector addition, v plus w. In other words, is there a distributive law? And the answer is yes. You get u cross v plus u cross w. Make sure you put the factors in the correct order. The cross product is not commutative, so it matters what order you write these factors. How about scalar multiplication? A times u cross v. Well, it turns out there is an associative property that you can define. You can associate the scalar a with either of the factors in the cross product, but only one. If you cross any vector with the zero vector, you will get the zero vector. If you cross any vector with itself, you will get the zero vector. Make sure you write that as a zero vector. Finally, how does the cross product behave in the presence of a dot product? What if you have u dot v cross w? Well, it turns out this is called the scalar. It is scalar valued because after you do a dot product, you get a real number. It's called the scalar triple product. And the scalar triple product is invariant under cyclic permutations of the factors. I'll tell you what that means in a moment. If you commute the factors in this product by shifting them down, and then when they get to the end, they bump off and go back to the beginning, that's called a cyclic permutation. A permutation is just a rearrangement. So 3, 1, 2 is a rearrangement of the numbers 1, 2, 3. It is a permutation of them. But that's not a cyclic permutation. The cyclic permutation bumps them down, and then when they get to the end, they cycle back to the front. We say that the scalar triple product is invariant, you get equality, under cyclic permutations of the factors. Do you see what I mean now? Before proceeding to a proof, let me point out that property 5 has a slightly more general statement. If we combine properties 3 and 5, if we say that the second vector is merely parallel to the first, then that would be a scalar multiple of the first. So if v is a scalar times u, then u cross v will be u cross a times u, which is a times u cross u, and we know that's the zero vector. So you end up with the zero vector. If two vectors are parallel, their cross product will be the zero vector. Let's get to the proof. Let's let u be the vector ABC. Now I'm going to stack vectors when I calculate this cross product, because then I don't even need to write the determinant. You can pretend there's an I, J, and a K above. U cross V will be BZ minus CY. Don't forget the preemptive minus from the middle cofactor, minus AZ minus CX. And then for the last coordinate, AY minus BX. Let's also calculate V cross U. To do that, we should stack them the other way. XYZ, ABC. With the I part, cross out the row and column, you get YC minus BZ. A preemptive negative on that middle cofactor, XC minus AZ. And then BX minus AY. You'll notice that the subtractions are exactly reversed compared to above. When you reverse the order of a subtraction, you get a minus out front. If you distribute the minus, you'll get a negative B and a positive A. So we will get a minus from each of these when we reverse the order, so we get the negative of U cross V. That proves the first property to be true. Property 5 follows very quickly from property 1. When you reverse the order, you get a minus. But if you have both factors equal to U, U cross U when you reverse the order gives you U cross U. If you move this to the other side, you get 2 times U cross U equals the 0 vector. Make sure that's a vector over there. Vectors equal vectors. You can cancel the 2 off, and then U cross U is the 0 vector. Property 4 was about crossing with the 0 vector. If I take, say, U equal to ABC and try to calculate U cross the 0 vector, I'll have I, J, K, A, B, C, 0, 0, 0. You see, I always end up with a factor of 0 on each term. And so if one factor in the cross product is the 0 vector, then the answer is the 0 vector. I'll let you prove the distributive law and the associative property with respect to the scalar multiplication. But we really do need to prove the invariance of this scalar triple product under cyclic permutations. That was property 6. Let's let U be ABC, V be LMN, and W be XYZ. Then what is V cross W? It is MZ minus NY, comma, preemptively put that minus for the middle cofactor in the second coordinate, LZ minus NX, and then Ly minus MX. If we dot that with U, we're dotting with A, B, and C. So we end up with A times mz minus ny minus b times lz minus nx plus c times ly minus mx, scalar. So we've calculated the scalar triple product u dot v cross w. We need to compare that with w dot u cross v, a cyclic permutation. So let's first calculate u cross v. U cross v, perfectly stacked. Bn minus cm. We have to usually put that minus. An minus cl. And then am minus bl. It follows then that w dot u cross v will multiply the coordinates of w times these coordinates and add them all up. We'll have x times bn minus cm minus y times an minus cl plus z times am minus bl. So the question we have is, are these equal? To test whether or not they're equal, we'll have to match like terms. We have, when we distribute, amz, a times m times z. Does that appear over here? Yes, a times m times z. So this term will match this term. We have a minus any. That's here, minus any. So the second term up here matches this term down here. We have minus blz, and down here we'll have a minus blz. So third, cancel these two terms. Minus minus makes plus bnx. We have a plus bnx down below. And then plus cly. Minus minus makes plus cly. So they cancel fifth. And then minus cmx and a minus cmx. And now we've matched all terms in the scalar triple product. We deduce then that in all cases, u dot v cross w is w dot u cross v. By the way, you can keep on permuting. We'll get v dot w cross u. You can see then that if we permute them the other way and bump around to the other side in the other direction, we still get invariance. So it doesn't matter which way you do the cyclic permutation, permuting the vectors to the right or to the left, whichever way works. I want to do some very basic examples. You need to have these in mind, and there's a specific way to think about them. I want to calculate I cross j. As you can see, this will be ijk. The coordinates of I are 1, 0, 0, and the coordinates of j are 0, 1, 0, by definition. What does this give? The I component gives you exactly 0. On the j component, you also get 0. But for the k component, crossing out its row and column, we get 1 minus 0. So I cross j ends up being k. There's something called the right-hand rule. If you point your index finger in the direction of the first vector in a cross product, and your middle finger of your right hand in the direction of the second vector in the cross product, then your thumb will point in the direction of the cross product. So if my index finger is in the direction of I, the middle finger in the direction of J, which is in the positive y-axis direction, then my thumb will point in the direction of the z-axis, in the direction of the vector k. This right-hand rule works even if the vectors aren't I, j, and k. But if they are, it tells you exactly which one to expect. For instance, if I have j cross k, what does the right-hand rule tell me I should get? Point your index finger in the direction of j, and your middle finger in the direction of k. You would expect to get I since your thumb is pointing out directly in front of you. We can prove this otherwise. I, j, k, the components of j are 0, 1, 0, and the components of k are 0, 0, 1. You can see that you'll get 1 in the first coordinate and 0 for the other two. That's I. Let's make a table. I cross I cross j, which we just proved was k, I cross k, j cross I. Remember that the cross product is not commutative, it's anti-commutative. It gives you a minus when you reverse the order. So if I cross j is k, then j cross I is minus k. Is the word anti-commutative a new word for you? We also sometimes say skew symmetric. It's not symmetric, it's skew symmetric by giving a minus sign. If you cross a vector with itself, you have to get the zero vector. We also just showed that j cross k is I. Let's see, we'll have k cross I, k cross j. By the skew symmetry, we'll have minus I here. And of course, k cross k is the zero vector. We only have to figure out I cross k. Well, if you use the right-hand rule, I cross k should be minus j. And so k cross I will be positive j. Now there is something to caution you about with respect to the cross product, and that is, it's not associative. To see this, I want you to look at some examples here. We'll do I cross the quantity I cross j and compare that to I cross I cross j, just a reassociation of the same factors. We know that I cross j is k, and I cross k is minus j, but I cross I is the zero vector. And if you cross any vector with the zero vector, you get the zero vector. Dun, dun, dun. You see that the cross product is not associative. So, nota bene. Nota bene. In Latin means note well. The cross product is not associative. You can't just move parentheses around in a cross product. So I think we have the algebraic properties pretty well down. The cross product is not commutative. It's kind of anti-commutative or skew symmetric. It doesn't satisfy an associative property, but it does have an associative property with respect to scalar multiplication. It does have a distributive law, just as you might hope. Also, the cancellation principle for the cross product is false. Normally, if I have AB equals AC, that's true if and only if B equals C. That won't be true for the cross product. If I have U times U cross V equals U cross W, that does not imply that V equals W. You can't cancel factors off of the cross product. That's false. Another thing that is normally true for products but not true for the cross product is the zero product theorem. Normally, if we have A times B equals 0, that implies A is 0 or B is 0. That's called the zero product theorem. But if I have U cross V equal to the zero vector, that does not imply that one of the factors is the zero vector. In fact, we've seen that if U and V are parallel, then their cross product will be the zero vector. Neither factor has to be 0. What's lacking in our discussion so far is any statements about the geometry involving the cross product. That'll be handled by our next theorem. First, the cross product of two vectors is orthogonal to both of the factors going into it. In fact, there is this right-hand rule I told you about. If you point your index finger in the direction of U and your middle finger in the direction of V, they don't have to be at a right angle. The plane containing U and V has a normal vector to it. Your thumb will point in the direction of that normal vector, which is in the direction of the cross product. The cross product will always be at a right angle to both of the vectors going in, and hence at a right angle to the plane containing those two vectors. Second, if theta is the angle between U and V, then the magnitude of the cross product is equal to the product of the magnitudes of the two vectors U and V times the sine of the angle theta between U and V. U cross V is the zero vector if and only if U and V are parallel. If and only if. The magnitude of the cross product, its norm, is equal to the area of the parallelogram spanned by U and V. What is the parallelogram spanned by U and V? Well, if I have a vector U and a vector V, we can parallel transport these vectors. This will also be vector V, and this will also be vector U. When you parallel transport these things, you end up with a parallelogram. The area of that parallelogram is equal to the norm of the cross product of U and V. To prove that two vectors are orthogonal requires that we calculate their dot product. Remember, we have a theorem that says two vectors are orthogonal if and only if their dot product is the zero scalar. So let's calculate u and dot that with u cross v. If u is truly orthogonal to u cross v, then this dot product must be 0. But remember, this is a scalar triple product, and the scalar triple product is invariant under cyclic permutations. So we end up with v dot u cross u, but u cross u we know already is the 0 vector. And if you dot the 0 vector with any other vector, you get the 0 scalar. That's the end of the proof for property 1. I'm going to skip the proof of 2 for now. We'll come back to it. But first, let u be parallel to v. That's true if and only if, say, v is a scalar times u. And that implies then that if I take u cross v, I'll have u cross a scalar times u, which is a scalar times u cross u, which is a scalar times the 0 vector, which is the 0 vector. So if they are parallel, then their cross product is the 0 vector. Also, we have to go the other direction. Suppose u cross v is the 0 vector. Now, if property 2 is true, then 0 will be the norm of u cross v, and property 2 says that is equal to the norm of u times the norm of v times the sine of the angle theta between them. We'll assume for this theorem that u and v are not 0 vectors. If that's the case, then these norms are not 0, and that will imply then that sine theta is 0. Well, if sine theta is 0, then theta is either 0 or pi, but that implies that these vectors are in fact parallel. The angle between them is 0, they're parallel, they're pointing in the opposite direction, they're still scalar multiples of each other, and they're parallel. So we've seen that property 3 depends upon the truth of property 2. The same is true for property 4. Let's look at that parallelogram spanned by u and v. How do you calculate the area of a parallelogram? Well, if h is the height, then the area is the length of the base times the height. Question is, how do you calculate the height? Let's suppose that theta is the angle between u and v. You can see then that h divided by the norm of v is opposite over hypotenuse when it comes to the angle theta. It's the sine of the angle theta, which means h is the norm of v times the sine of theta, and that gives us that the area is the norm of u times the norm of v times the sine of theta. And if property 2 is true, that's the norm of u cross v. As you can see, everything comes down to the truth of statement 2. We need to prove that next. Statement 2 says the norm of u cross v is equal to the norm of u times the norm of v times the sine of the angle between u and v. So here's how we're going to prove this. We're going to take the norm of u squared times the norm of v squared times sine squared theta. It's sufficient to show that the equation is true even if both sides are squared. But because of the Pythagorean identity, sine squared is 1 minus cosine squared. Now, remember that cosine theta is u dot v over norm u norm v. So we are going to have norm u squared norm v squared times the quantity 1 minus u dot v squared over norm u squared norm v squared. Now, distributing to the two terms inside of the parentheses, we have norm u squared norm v squared minus u dot v squared. Does that equal the norm of u cross v squared? Well, let's suppose that u is the vector ABC and v is the vector XYZ. Then u cross v is BZ minus CY. Preemptively put a minus on the middle coordinate, AZ minus CX, and then AY minus BX. We need to show that the norm of this vector is equal to the expression that we had last. To do that, I'm going to use the computer. We need to show, we want to show that BZ minus CY squared plus, when we take the norm, we square the coordinates. This minus will get squared away. AZ minus CX squared plus AY minus BX squared is equal to, the norm of u squared is a squared plus b squared plus c squared. The norm of v squared is x squared plus y squared plus z squared minus the dot product squared, which is ax plus b y plus c z quantity squared. So the question is, do we get equality here? I don't know about you, but I'm too lazy to check this by hand. I'm going to make my computer do it for me. So here's what we're going to do. We're going to subtract both sides of the equation and see if we get 0. Now, on the right-hand side, we had the norm squared times a norm squared. I'll put in the squares here. Minus a dot product squared. The dot product was a times x plus b times y plus c times z. The second norm was x squared plus y squared plus z squared.
And the first norm was a squared plus b squared plus c squared. Since we're not doing square roots, we should leave these unsquared. They're already squared because we took off the square roots. Now, in the first box, we'll have some terms all added together and squared. We square the three coordinates of the cross product and add them up. We would take a square root, but we're doing the square of this norm, and so that cancels the square root. The first term was b times z minus c times y. The second coordinate was a times z minus c times x. And the last coordinate was a times y minus b times x. All right, it all comes down to this. If we get 0, then the two sides are equal. If we don't get 0, then we screwed up. Ta-da! The computer tells us it's 0, so the two sides are in fact equal. By the way, is this your first proof by computer? As an example, find the area of the parallelogram having vertices, let's say 0, 2, 1, and then how about, let's say 1, 4, 4, and then 3, 4, 2, and finally 4, 6, 5. I claim that these are the vertices of a parallelogram. Well, that's going to be pretty difficult plotting this in 3 dimensions. Point 0 on the x-axis, 2 on the y-axis, and 1 on the z is right here. We'll call this A, B, C, and then D. Point B is 1 unit this way, 4 units along the y, and then 4 units along the z. If this is A, this is B. Then we have 3 units along the x, 4 units along the y. 1, 2, 3, yeah. And then 2 units in the direction of z, that's the point C. And then 4, 6, and then 5. 1, 2, 3, 4, 5. The point D, somewhere about here. Does it look kind of like a parallelogram, maybe, kind of, sort of? Well, I defy you to calculate the area of that parallelogram any way than the way that we're about to do this. What we'll do is we'll calculate vectors AB and AC. They form 2 edges with a common vertex on the parallelogram. Then we can calculate the area of the parallelogram by taking the norm of the cross product of those 2 vectors. So first, let's write down the vector AB, which I'll call U. We'll take the coordinates of B and subtract the coordinates of A. That gives us 1, 2, 3. Now, the vector V is going to be AC. So we'll take the coordinates of C and subtract the coordinates of A. That gives us 3, 2, 1. So first step, let's calculate U cross V. That's going to be 2 minus 6 is negative 4. We'll get a preemptive minus on the middle one. 1 minus 9 is negative 8. And then 2 minus 6 is negative 4. We'll get a little more efficiency if we factor a 4 out of this. The area is then the norm of U cross V. Well, when I take the norm of 4 times the vector negative 1, 2, negative 1, note that the 4 can come out in absolute value, but it's already positive, so it comes out. What's left is 4 times the square root of negative 1 squared plus 2 squared plus negative 1 squared. That's 1 plus 1 is 2, plus 4 is 6. The area of the parallelogram is 4 times the square root of 6. It turns out there's a special interpretation, geometric interpretation, of the scalar triple product. It's contained in the next theorem. The volume of the, you're going to love this word, parallelepiped spanned by 3 vectors u, v, and w. Okay, what is the parallelepiped spanned by 3 vectors u, v, and w? If u and v are down in the plane here and w comes out like this, then we'll parallel transport these vectors around and obtain the parallelepiped spanned by u, v, and w. If this is u, this will be u here. If this is v, this will be v here. W, 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 w on each of those corners. It turns out the volume is the absolute value of the scalar triple product. Well, how are we going to prove that? Keep in mind we have u, v, and w poking out over here like this. In order to calculate the volume, what you can do is you can get the area of the base and multiply that by the height. So the volume is the area times the height. Well, the area is pretty easy to do. The area is the norm of u cross v. The question is, how do we calculate the height? Well, we do that a very sneaky way. Whatever u cross v is, u cross v is going to be poking out at a right angle to the plane containing u and v. In other words, it's parallel to this height over here, because it too is at a right angle to the plane. So what we can do is we can project w onto u cross v. The projection onto u cross v of the vector w. If you calculate its norm, the norm of the projection, that must be the same as the height. So this is going to be the norm of u cross v times the norm of the projection onto u cross v of the vector w. Well, what's that? Remember that the projection of u onto v is u dot v over norm v squared times v. So we're going to have the norm of u cross v times the norm of u cross v dot w over the norm of u cross v squared times the vector u cross v. Scalars can come out of norms in absolute value. This will cancel one of those. The rest of this can come out in absolute value. We'll write it as w dot u cross v in absolute value. We'll still have one factor of the norm u cross v in the denominator. The only thing left inside of the norm now is u cross v, which exactly cancels. Now, by the invariance under cyclic permutation of the scalar triple product, we have the absolute value of u dot v cross w as suggested. For example, find the volume of the parallelepiped spanned by u equals 1, 3, 2, v equals 2, 0, 4, and w equals 3, 1, 2. The first thing we need to do is calculate v cross w. And since they are stacked like this, that's easy to do. It's 0 minus 4. Put a preemptive minus on the middle. 4 minus 12 is negative 8. So a negative negative 8 gives us a positive 8. And then 2 minus 0. If we then calculate the scalar triple product, we'll take 1 times negative 4, 3 times 8 is 24, and then 2 times 2 is 4, for a grand total of 24. Since that's already positive, that is the volume. There's one more concept that we have to discuss in this video, and that is torque, or moment. Suppose we have a lever arm from point P to point Q. We'll have the vector PQ. We're going to apply a force right here at the tip of the vector PQ. And we're going to assume that this is fixed at the point P to rotate around this point. What is the torque or moment that results from this? The moment of the force F applied at Q about the point P is, we'll denote this force, this torque, this moment, by tau. It is a vector quantity. It will be the lever arm PQ cross the force F. So for example, Let's suppose I have a bicycle pedal and it's currently at, say, 30 degrees from the horizontal, and I'm applying a force. Let's suppose I'm applying a 75-pound force at an angle downward 45 degrees downward. So this is my force, and this is my lever arm, PQ. First of all, what is PQ? How long is this lever arm? It's a bicycle pedal. Let's suppose that it's 9 inches, which is 3/4 of a foot. The magnitude of that vector then is 3/4. Its coordinates are going to be cosine of 30 degrees, sine of 30 degrees, and then 0. We'll pad it. With a 0 for the final coordinate. If you have things lying in the plane, you can always add a 0 for the z coordinate. For the force F, it's 75 pounds. The angle is negative. It's going to be cosine negative 45 degrees, sine negative 45 degrees, and then, of course, 0. The vector PQ is then, well, let's see, cosine of 30 degrees is the square root of 3/2. So you get 3√3/8. The sine of 30 degrees is 1/2. We'll have 3/8, and then 0. For F, we'll have to distribute the 75. The cosine of negative 45 degrees is √2/2. So we'll have 75 √2/2. The sine of negative 45 degrees is negative √2/2. So we'll have negative 75 √2/2, and then 0. What is the torque? It's the cross product. It's PQ cross F. Well, these are nicely stacked, so we can do this easily. We get 0 minus 0, and then 0 minus 0. It has to have only a z coordinate because it has to lie perpendicular to the plane containing PQ and F. And then the last coordinate is going to be, let's see, that's kind of complicated here, 3√3/8 times negative 75 √2/2 minus 3/8 times 75 √2/2. So that gives us 0, 0. Here we're going to have negative 225√6/16 minus 225√2/16. And that is the torque. Our next video will have a number of applications of the cross product.